Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Maths 3, Iterations and Vectors, Part 1, Iterations. Now I've put iterations and vectors together because they don't really go with anything else. So this will be the iterations part, and then part 2 and 3 will move into the vectors part. So want to do iterations today. It is a question type all to itself. And usually what we're going to see is these question types have 3 parts to them. Usually they're in 3 parts. The first part is a review type part. In other words, it correlates with something that you've learned previously, even back to Pure Maths 1 content. And you start there and it leads up to the iterations part, which is the second and third. So that first one is a review, really difficult to plan for because it can come from any previous thing you've learned. Then the second and third parts are quite consistent. In the second part, you do what's called a decimal search. And then in the third part, you do the actual iterations formula itself. So we'll look at these a little bit later. Right now, I want to help you understand the concepts before we move into the skill part. So the concept of what is an iteration and why do we do it? So let's take an equation x squared minus x equals 0. And if you're solving it, it's very easy to find the roots. You can just factor it, set equal to 0. And so we see that the roots are 0 and 1. And so this we know would be a parabola. It would cross the x-axis at 0 and at 1. But let's say that we are not after roots that are integers or even fractions. Let's say we're after roots that are irrational. They're going to be decimals. Well, that's a lot harder to find, and you can't find it simply by factoring. And we're going to be dealing with equations that are far more complicated than quadratics. So if we were dealing with irrational roots with quadratics, we just use the quadratic formula. But once we get out of quadratics to exponentials, trig functions, logarithms, or higher polynomials that are irrational roots, we need a method for finding those roots. Now, while we could have graphed this, let's just say that this graph is too complicated for us. So if this graph is too complicated for us, one way that we can simplify it is to break it down into 2 recognizable parts on each side of the equal sign. So if we add the x to the other side, we get x equals x squared. So this one is a lot easier to graph. It's just the y equals x line and also the y equals x squared. And here I've drawn half the parabola and the y equals x line. So we can draw both of those. Those should be familiar graphs, and you can see it right here. And you can also see now the roots are not where it crosses the x-axis. The roots now are where these 2 graphs cross each other. So with the original, it's where it crosses the x-axis. With this one, it's where the 2 separate graphs cross each other. We see that they cross at 0, and they also cross at 1. But let's say instead of solving for this x, what if we solved for this x over here? So we still add the x to the other side, but we want to solve for this x. So we square root both sides, and we get x equals root x. So again, we've got 2 recognizable graph types here. We have the y equals x, and now we have the root x, which goes like this. So what do iterations do? Well, what iterations do is it works its way toward that root to a level of accuracy that you want. Now, there are going to be two things that can happen. Either your answer will converge to a particular value, which is what you want, and when it converges to a particular value, that value then is the root or estimate of the root. If it diverges, meaning the value of your question just goes off in no particular direction at all, then that is not helpful. So if you have a divergent situation, just rearrange for a different x in the formula, solve for a different x, and then hopefully you'll have a system that converges. Okay, here we have two separate graphs that come from these two different ways of solving for x from this original equation. If we look at this one here, what you do is you pick a starting point. So you pick a starting point and you call it our original x value. Now, actually, in the decimal search part, you're going to establish your guidelines. You're going to establish that the root is between two numbers. And so you'll start with the lower number in your calculation. But if you don't have that guidelines, then you just have to pick a random number, although shouldn't say random. You can look at the graph and intelligently pick a value that looks to be close to it. So here's the root that we want to arrive at. Now, the example I gave has rational integer roots, but let's just pretend that these roots are irrational and we don't know what they are. So we're trying to reach this point here and find out its decimal value. So we pick a number for x. So here it is up here, our original value of x, and we're going to plug it into the equation, meaning in this case we're going to square it, and that's going to give us our x value. So here we put in the x and we follow it up, and that gives us the y value. Well, this y value is equal to the y value on the other side. It's y equals x and y equals x squared. That means the y's are equal to each other. So this y value is the same as this y value over here. And this y value, because it's on the y equals x line, is equal to a particular x value. That x value then becomes the next round in our iteration. So when you make one complete cycle, that is one iteration. So you start at original x, you square it, that becomes your y then becomes your next x, and that is now your x1, your first iteration. And you plug it in again and you keep going around. But if you notice, when we put in our x and we got our y, and our y came over here, we're going away from the value that we want. So this one actually diverges and does not help us achieve the goal that we want. So let me just show you really quickly in here what it would look like in your calculator. So you start off, and let's take the value 0.5, and we're going to take 0.5 and we're going to square it, because that is our function x squared. So we put in there the 0.5. Hopefully you can see it there. It's a little dark. 0.5 squared. Maybe I can lower this down to get a little bit more light here. So 0.5 squared. And then when you hit equals, you get 0.25. Notice it's getting smaller. We actually want it to approach 1, but it's going away from 1. And so what you would do is you would go back, and instead of plugging in 0.5, you can just delete it and plug in the answer. You notice there it says answer squared. And we hit the equals 2 for that. And now it's 0.0625, and you can keep hitting the equals to, but it keeps getting smaller. It's not approaching any particular value. It's diverging. It's going away from the value that we want. Now let's come over here to this one. This one here is going to be the one that's going to work. And notice both of them follow the x equals f of x format. This is like the formula or the format that you want to get your original equation into to do the iterations formula. It's what allows this circular thing to work. You got to set them equal to each other so that the y's are equal to each other. So in this one, we're going to pick an x for this one here, our function of x. So here is our value that we pick, our original value of x. We plug it into the root x, we square root it, and it gives us a y value. This y value is the same as the y value up here. This y value is now our next x, and the next x is what we plug in to the equation again, okay? So here is our original x. We plug it in, we get a y value. It's the same as the y value over here, and that gives us the next x. When we plug that one in, it gives us the new y value, which is the same as the y value over here, and that gives us the next x, which when we plug it in gives us this y value and is the same as this y value over here. So these are the different y values, corresponding y values there. And notice we started here and we're getting closer and closer to the root. So let me show you what that looks like with this one. Remember, we started with 0.5. So we'll start with 0.5 again, but this time we'll use this one instead of this one up here. It comes from the same original equation, but just rearranged differently. So here you can see you get 0.5 inside the square root. You get equals, and now you get 0.707. So let's go back to our radical, delete the 0.5 and put in answer. So you put in the answer and now hit equals. And now we have 0.84 and we hit equals again, 0.917, hit equals again, 0.957. Notice the more times you push it, the closer and closer it's getting to 1. Now it's 0.9945, 0.9972, and it's getting closer and closer to 1, which is the root that this particular graph shows, although the examples that you're going to solve are not trying to approach an integer. It's trying to approach a decimal or an irrational value. And so you're just going to take it accurate to 3 or 4 decimal points. Okay, so that's what we're going to do. Now, I'm going to, hopefully that helped you understand the concept. It takes a little bit of getting used to thinking about what all that means. The actual skill of doing this, or at least for parts 2 and 3, are pretty easy. The review part is also good for you so that it connects with previous things that you've learned. So let me clean up the board a little bit, and I want to take you through some of these review. We're not going to actually solve them, but I want to help you identify some of the review type in the first part, and then also show you the consistency of the second and third parts. Okay, what I'm going to do is I'm going to take you through each question from the year 19. So summer of 19 has 3 questions, winter of 19 has 3 questions, 1 question per paper. And I'll take you through each of those just to show you that first review part. And I'll tell you where you can find how to solve those. It should be something you already know how to do, but you might need to look it up. And then we'll focus on the second and third part, which is the new material for this particular lesson and for this video. So let's go to share screen. Here we have, notice this is summer 19, paper 31, number 7, summer 19, paper 31, number 7. And here's the first part here. The first part shows this graph, says the diagram shows these two curves, gives you the equation of both curves, and it says that the tangents to the curves are perpendicular. Well, we know that this is from Pure Maths 1, differentiation, the tangent normal. So if you go back to Pure Maths 1, differentiation, tangents normal video, then what you would basically learn is you take the derivative of this one over here, which would help you to find its slope at point A. So you're plugging in a variable, and you take the slope of this one here and also plug in A. But since it says that they are perpendicular, then one of them, you're going to do the negative reciprocal and you're going to set them equal to. So the slope of the one on the left set equal to the negative reciprocal of the slope on the right when you put an A in for the X. Then you'll cross multiply and solve it for A, and you should end up with this right here. Notice it is a show problem. Most of the first ones are show, because in case you can't solve the first part, this is your starting point then for the other two parts that you want to get into. Okay, so this one correlated back to Pure Maths 1, differentiation, tangent, and normal. Now the other two parts will be quite consistent. Here you see verify by calculation that A lies between 2 and 3. And most of the time, Cambridge will give you these boundaries to check. Now, in case they don't, you need to go back yourself and look at this point of intersection between the lines. That is the root that you're trying to figure out. And here you see a 4 over here. So even if you used 0 and 4, at least you would have some sort of a boundary. But the further away that you are from it, the more iterations you'll have to do in the third part. So this gives you 2 and 3 as boundaries. It's a little bit more narrow from 0 and 4. And so what you're going to do is, we'll talk about the part 2 and 3 later, but I just want to see that this is what it looks like. And then the part 3 is to use the iteration formula. So we'll actually get into those a little bit later. What I want to show you now is these first parts and how they correlate to different material. So that was summer 1931. If we look at summer 1932, this one, summer 1932, number 6, correlates again back to Pure Maths 1. And if you're looking for the video, it's in the trigonometry section, and it's about circular measure. So it's called circular measure. The old curriculum called it radians, but the newer curriculum calls it circular measure. And if you're looking for the video, it's in the trigonometric videos part. And so you'd have to solve this. Now, this one happens to be a 2-part review. And so here's where you do the show. And then here's the verify the calculation lies between 1 and 1.5. That's our decimal search. And here again is the iterative formula. So the last 2 parts are very consistent. It's the first one that's going to change depending on the correlation. Here's summer 1933, number 6. And this one has a polynomial going across the x-axis. It gives you a polynomial and says that b is an integer. You actually have to take the factors of 6 and the plus or minus factors of 6, which obviously b is positive. So really you only need to take the positive factors of 6 and divide those through, or just check the polynomial, the function of those, take the function of those positive roots and see which one gives you a 0, meaning it's a root. And so you can find the value of b that way, but it corresponds to pure mass 3, further algebra polynomials, if you're looking for the video that would cover this kind of a thing. Then the second part, again, here you have to show how to get a by itself. So you're going to have to rearrange this polynomial, and notice the x occurs in 3 different places. You're going to have to figure out which one of those x's you're actually solving for. So you might want to do a little bit of forwards, backwards. You got both ends. You got to figure out how to fill in the middle and to show that you get this. And then here is the iterative formula. So this third one, iterative formula, is the same. The second one is a little different. It wasn't a decimal search. Instead, it's rearranging it. So they want you to rearrange it into this form. And the first one, again, was the correlation part. Now we move on to winter 19. Here's winter 1931. So we'll come back and look at these a little bit more here. So on this one, notice stationary point. So stationary point is derivative or differentiation. But this differentiation is the product rule. Notice we have an exponential and a logarithm. So this was from pure mass 3 differentiation using the product rule to find your stationary point. And then you got to show that that turns into this form here. Then the second part is verified by calculation this. And we're going to actually come back to this one. So I'm going to leave this one here. Let's look at the next one. This is winter 19, paper 32. And if you look at the first one, this one is an integral. So you're starting with an integral. And notice there's unlike terms, x and cosine x. So a product of unlike terms. This is going to be an integration by parts, which was also pure mass 3. In fact, we just did that a few videos ago. Integration by parts. And then you get a by itself and try to get it into this form. So every single question has had a different lead-in correlation to something in the past. But when you get to this, you still have x as a function of x or a as a function of a. Then here is the verified by calculation and the iteration. So we'll come back to this one as well. And there's one more in here. Here's winter 1933. Notice this one is sketching. So sketching a suitable pair of graphs. They've already split the original into 2 sides. So you have a ln on one side and an exponential on the other. So this is pure mass 3 transcendental functions, exponentials and logarithms with the focus on sketching. So you might even be able to find this example in the video. But again, that's the lead-in. And then here's the calculation and the iteration after that. So we'll come back to that one as well. But let's do this one here. So here was the, here's the form that we're starting with. By the way, this EXP means e to the x. So this is actually an e, and all of this in parentheses is the exponent. So let's come back to the board here. Come back to the board. So here is our 1 plus e raised to that parenthesis is the exponent. And actually this one right here, this is the form of x equals f of x. That's our general form for iteration, x equals f of x. And so x equals f of x. And what we want to do for decimal search, it's very important to remember this, because the form is set up for iterations, but you need to change it for decimal search. For the decimal search, you need to put everything on one side and set it equal to 0. So you're going to take this x and subtract it to the other side to make it equal to 0. Don't forget to do that for decimal search. because normally they give you the form in iteration form, not for decimal search. So subtract the x to the other side, and it said between 2.2 and 2.6. So we plug in 2.2 in and we calculate it. So our function of p, and asking for p, letter p, the function of p, this is our function because it's been set equal to 0. 2.2, you plug in for the x and you get 0.317. And when you plug in the 2.6, you get a negative 0.233. The thing is about a root, remember the root is right on the x-axis. So if your graph is going through the x-axis, then that means on one side of the root, you'll have, say, a negative, and on the other side of the root, you'll have a positive. Or the other way, you might have a positive first and then a negative. But as it crosses the x-axis, which is your root, then your signs will change. That is what you're looking for in this decimal search, is the sign change. So all you need to do is plug in those two endpoints of the boundaries they give you. You record the values and you see there's one positive and one negative. And all you have to do is put, there's a sign change. Therefore, the root has to be somewhere in between. Okay, the root is going to be right at the 0. And so in order to go from a positive to a negative, you have to cross the x-axis. You have to cross the 0. So there's a root somewhere between 2.2 and 2.6. So that's the decimal search part. Then it says to do the iteration. Let me just show you really quickly the question. So here's, we did the verify by calculation that p lies between the two. Now we do the iteration part. Use the iterative formula, that's the x equals f of x, and determine p correct to 2 decimal places. Give each iteration to 4 decimal places. So we're coming back to this form here. This is our x equals f of x. We're choosing a value for x. So if you don't know how to interpolate, you can just start with the lower boundary and work your way up. Notice the 0.3 and the 0.2 are almost halfway in between. So you could start at 2.4. If you interpolate it first, it can save you about 2 steps of this iteration process. But if you're not comfortable with interpolation, then just start at the lower end and work your way up. Most likely you're going to reach it in about 5 or 6 iterations anyway. So you start with the lower end, the 2.2, that's your original number. You plug it into the f of x, and that's going to give you your new x. Actually, this gives you the y value for this side, which happens to be the y value of this side, and your y also equals your x, and so your x becomes the next value that you plug in again. So we're plugging in a 2.2. When you plug that in, you get 2.5169. So then you would plug in 2.5169, but on your calculator, just go back, delete the 2.2 and insert answer on your calculator so that you don't have to keep retyping in all these numbers. So I hope you saw how I did that in the previous example. So if I do that really quickly here, just so that you can see, oops, don't want line, want e raised to the 1 divided by 2 times x minus 1, x is 2.2 minus 1. So here you can see that I have 1 plus e raised to the 2 times 1 over 2 times 2.2 minus 1. You hit equals. There's your 2.5168. Remember, you're taking this to 4 decimal places, so it actually rounds up to the 9, 2.5169 to 4 decimal places. So this number you now need to plug back in there. So just scroll back with your arrow key to your 2.2, delete the 2.2 and insert answer. insert answer. Your answer was the 2.5169. So you just insert answer and then hit equals. And there's your 2.3904. 2.3904. And now all you have to do is hit equals again because you already have answer in there and your answer changed. So you just hit equals again. And now it's 2.4327. Make sure you write that down before you hit equals again. 2.432, and it actually rounded up to 8 because there's a 5 after the 7. Then hit equals again, 2.4176. And so we have that one right here. And then we hit equals again. What we're looking for is for it to be accurate to 2 decimal places. Each iteration, obviously the first one does not have 4 decimal places. It's just your boundary. But these iterations need to have 4 decimal places. And then we want to make it accurate to 2 decimal places. So notice we have 5-1, 3-9, 4-3, 4-1. We want that to become consistent. So now we get 2.4229. And then we hit equals one more time. And we have 2.4210. So we can see that for the 2.42 is accurate to 2 decimal places. This isn't going to go any higher. This one isn't going to go any lower. It's kind of oscillating back and forth as it gets closer to that exact value or that approximated value. And so we now have it accurate to 2 decimal places, so we can stop the iterations and say that P equals 2.42 and it's accurate to 2 decimal places. So what we're looking for is this right here, 2 decimal places, and see that this is not going to round up, and obviously it's not going to round down either. And so we're safe at 2.42. Okay, so that's our first example. Let me set up for the next one. Okay, let's look at our second example here. And here we have again, this was the first part up here. We're on the winter 19 paper 32. We already looked at this. You have to do an integration by parts. So you can go back and look at that video. Then we have verify by calculation that A lies between 2.5 and 3. And then the iteration part is 3 decimal places for the final answer, 5 decimal places for each iteration. So pay close attention to the number of decimal places you need it accurate for the final as well as for each iteration. So we have 3 and 5. So maybe the concept of iterations or how iterations works might be a little difficult to grasp, but hopefully you see that the decimal search and the iteration process itself really isn't that difficult. You're letting the calculator do most of the work. And you do have that entry level first part that reviews other topics that you've covered before. So here it gives us the show result there from that first integral that you were supposed to do. So this is our A as a function of A. This is set up for the iteration. So don't forget, for the decimal search, you need to set it equal to 0. So we subtract the A to the other side, set it equal to 0. They gave us the boundaries, 2.5 and 3. When you plug in 2.5 into this equation that's set equal to 0, you get 0.179. When you plug in the 3 into this, oh, by the way, this is in radians. I don't know if you caught that by looking at the domain statement in part I. But if you looked at the domain statement in part I, it had pi in it, which means that you need to set your calculator to radian mode. So make sure your calculator's in radians. And so you plug these values into this equation, you get these 2 numbers, one positive, one negative. So you say there's a sign change. Therefore, your root A has to be between those 2 numbers. So that's easy enough to do. Your calculator does the work. The main thing that you have to remember is to set it equal to 0, because the form is set up for iterations, not for the decimal search. Then for the iterations part, where we use this, we want 3 decimal points for the final, 5 decimal points for everything in between. We start with the lower end, 2.5. Notice it takes 6 iterations again. If you look, these are almost identical. So if you were to interpolate, now the interpolation doesn't work perfectly because when you interpolate, you're assuming it's linear. This is not linear, so interpolation is not going to be a perfect match. So don't spend too much time trying to be technical about it. But if you can do a quick mental interpolation, and you see that 0.17, 0.17, it's basically symmetrical. So you want somewhere in between, like 2.75 would be a rough estimate. So if you start with 2.75, notice 2.75 is a little too high, so you'd have to come back down a little bit. But 2.736 is closer to 2.75 than it is to 2.5. So you might save yourself a step or two if you do a quick interpolation, but you don't have to. If you're not comfortable or don't understand how interpolation works, again, it's not perfect anyway because it's not linear, but it can save you 1 or 2 iterations of work. But we'll start with 2.5. And so you plug it into this one up here. Don't plug it into this. Plug it into up here on the function side. And when you plug in 2.5, you get 2.67877. That becomes your new value that you plug in. Again, delete the 2.5 and hit answer. Put answer from your calculator. So when you hit equals on that one, you get 2.71994. Hit equals again, 2.73142. Hit equals again, 2.73474. So a lot of your time is actually spent writing because your calculator is working as fast as you hit the equals button. But you got to write out each 1 to 5 decimal places. Make sure that the 5th one is rounded accordingly to what follows it. So 2.73572. 2.73600. So when we're looking at 3 decimal places, here we have 2.735, and the 7 will round it up to a 6, and here's 2.736, and it's not going to go any lower than the 0. So here we have 6 at the low end, and we have rounds up to 6 on the high end. So 2.736 is accurate to 3 decimal places. Okay, so let's look at one more just to make sure you get this pattern down. And let me set up for that. Okay, let's look at the last one for this video here. And it says, notice this was the sketching one. So when you sketch the 2 graphs, the logarithm and the exponential, again, you might have to go back to the P3 transcendental functions, exponentials, and logarithms sketching video. And they're going to intersect at a particular point. Then it wants you to show by calculation that this root lies between 1 and 1.5. And then it says, using the iterative formula, they provide it for you to determine the root correct to 2 decimal places, give the result to 4 decimal places. So let's go back to the board here. Actually, this was like the first one they gave, or they moved this 4e to the negative x on the other side. When you do the decimal search, you actually can either use the original function, or you can use the iteration one, but you need to make sure you subtract x to the other side, set it equal to 0. So they're really the same thing, they're just rearranged. So this one is more like the original one. And so uh, they had these two graphs. You graph the ln on one side, the exponential on the other. So I just moved it, set it equal to 0. So you can either go from the original, or you can go from the iterative form, but make sure you subtract the x to the other side so it's equal to 0. You can do the decimal search from either one. Your numbers will be different, but you'll still get a sign change. And in the mark scheme, you might see two sets of numbers. One set of numbers is if you use the original as your plug-in point, and the other one is if you use the iterative formula as your plug-in point. So I think I used this one up here. And so f of 1, because it said between 1 and 1.5, is a negative 0.373. F of 1.5 is a positive 0.360. There's your sign change. Therefore, x falls between 1 and 1.5. We know that the root is somewhere in there. We can see this again is almost symmetrical. So I might start at 1.25 if I were interpolating it, but you don't have to. You can start at the lower end. So let's start at 1. Now we're working with the iterative form, the x equals f of x, or some function of x form here. And when you look at this one and this one, by the way, they solved for this x right here. Here's they added this to the other side. They divided it by 4, and then they ln'd both sides to get rid of the e. And then when you divide by the negative on your logarithm flips the fraction upside down. So it was ln x plus 2 divided by 4, and that little negative, when you divide it at the end, flips it upside down to 4 over ln x plus 2. So they rearrange this. Sometimes they ask you to rearrange it. So it'd be a good idea for you to mentally check and see if it makes sense, because sometimes you have to do it. So you should have that practice for that. But they solved for this x right here, not for this one. This is the one they solved for, got it by itself. So they provided it in this case. So we need the final answer to 2 decimal points and all the iterations to 4. So we're going to start at the lower end, which is 1. You plug that in and you get 1.2922. Plug that in again, or just change it to answer. Click your calculator, the equal sign, and you get 1.2110. Again, make sure that you are rounding that 4th decimal point. Check the number after it if it rounds up or not. So make sure you're checking those 4th numbers. And then you get 1.2322, 1.2266, 1.2281. So here we can see here it was 21, 23, now it's 22 and 22 again. So we can see that this one, the lower end is going to round it up to 3, and the upper end, the higher value, will also round it up to 3. So this is kind of going back and forth. Started way up at 1.29, down to 1.21, up to 1.23, down to 1.226, up to 1.228. But it's safe to see here that it's going to stay between 6 and 8, which means this will always round to 1.23 with that. And if you want to, for fun, you can just keep hitting equal to on your calculator to see that whole number across your screen will eventually equalize out. And that's basically your irrational root for where this crosses the x-axis, or when you move this to the other side where your logarithm and exponential cross each other in the sketch. So I hope this helps. Again, I hope you see that these are quite easy to identify, the question type, because in that third part says iteration. The first part, this is the part that is more up to you on how well you remember things that you've learned in the past. We've seen sketching. derivatives, integrals, polynomials, all sorts of things can be that lead-off question, and sometimes they're worth half of the points. So you really need to practice your review and do well on that. But I left that to you. I told you the videos you could look at for help. Then the decimal search is easy as long as you remember to subtract that x to the other side and make it equal to 0. Then the iterations, just start at the lower boundary and work your way towards your accuracy that is indicated, and just pay attention to the decimals. All you're doing is writing down the numbers. The calculator does the work for you. So I hope that helps. That's iterations. And thank you for joining me in the Zoom room. Hope to see you again for the next video where we start into the vectors.